Good morning and good afternoon to everyone, depending on where you're joining us from. So thank you for joining today's webinar on materials impact on high-speed, high-frequency performance. Today's webinar is being presented by DuPont Silicon Valley Technology Center, located in Sunnyvale, California. So before I introduce our two speakers, I would like to cover a few housekeeping topics. Today's webinar will be recorded, and we will share a link in the coming days to all the registrants. We also welcome you to revisit the content yourself or share it with colleagues. We also invite you to ask questions. Please look at the Q&A box on your control panel. And if you have any questions for the speakers, just type it into that box at any point in time. The speakers will address as many questions as time permits at the end of the presentation. So today's presenters are John Andrzakis and Jack Frankowski. John Andrzakis is a senior technology consultant for DuPont, and he joined the company in January of 2018. He has over 40 years of experience in the manufacturing of printed circuit boards and related products. He currently is concentrated on identifying opportunities in the high-speed, high-frequency markets, as well as helping to shape the efforts of the R&D team on developing new products. Jack Frankowski is a business development leader for DuPont. He joined the company in November of 2018. And Jack has over 34 years of experience in RF, microwave, and wave design, development, and manufacturing of material setup in printed circuit boards. And at this time, I'm going to hand it over to Jack Frankowski, who is going to start today's presentation. So good morning, Jack. The floor is yours.
Good morning, good afternoon, good evening. I wanted to move through with a short agenda on the topics I'd like to cover today. And in covering what our materials bring to impact high-speed, high-frequency performance, I wanted to cover this from a couple perspectives. One is a broad view of the material factors affecting loss in a typical transmission line. We're going to go over some modeled and measured performance for typical test vehicles as well as some differential pairs. The aim in bringing these materials to this kind of application is to drive more data in the same space. So there's going to be a couple slides on how these tasks are performed, and in doing so, we're going to be comparing conventional and new materials in some of the test vehicles and in some of the modeling. So what we'll show with our materials is how their technical benefits enable higher data rates. The physical properties that we'll bring offer favorable geometry to circuits by way of lower dielectric constant, as an example. And by leveraging these, it's possible to get more data capacity in a given channel, improve results for conventional digital, as well as PAM4 and other advanced modulation protocols. And it's likely that some of the boards can take advantage of the materials to enable longer channels and possibly fewer components in the bill of materials. So at our Silicon Valley Technology Center, we've got a variety of capabilities for characterization. There are resonant cavity methods for characterizing materials directly. The Fabry-Perot resonator, split post dielectric resonator, split cylinder, and thin sheet testers. These are connected through our vector network analyzer, which has capability up to 125 gigahertz. And again, we're testing materials in a resonant arrangement so that we're concentrating energy in the material and assessing its loss characteristics in a high energy environment. We've also got, with our vector network analyzer, the capability to test circuits. So not just direct materials characterization, but the characterization of materials by way of a test vehicle that looks like a printed circuit board, or in some cases, some actual printed circuit boards. And we can do this through the capabilities of the S parameters, as well as looking at circuits through time domain reflectometry. The other equipment that we've got is an impedance analyzer, and this enables us to characterize materials and circuits and take a look at impedance and bear out dielectric constant dissipation factors. And the probe station that we've acquired is something that is targeted at the millimeter wave frequencies, where some finer line geometries are used for test vehicles and circuits that are used in that frequency range. And again, that'll hook up through the VNA, and we're employing these techniques to a greater extent in characterizing existing materials and products and new product development. So some of the broad view, some of the contributors to insertion loss include the conductor, dielectric, and radiation, just the three big buckets on this. Some of the facets to conductor's contribution to insertion loss include its surface roughness, and a lot of time spent on this in various models. A lot of concentrated efforts are being used by the manufacturers of copper foil to bring better products to the market. We need to see how all these are going to interact with our material sets. And again, in testing these copper foils, it's necessary that we put it together in a circuit type of arrangement, make a test vehicle that looks like a printed circuit, and we get the performance of the system that way. The dielectric is another important contributor. We're going to look at the contribution of dielectric constant and how designs can leverage different dielectric constants to get better performance or more favorable geometry. Dielectric loss is something that we're striving for lower figures in this space, and it's a material property that we're measuring so we understand how it's going to contribute to the system. Dielectric thickness, along with dielectric constant, it's a design choice to an extent. There's an impact on going to a thicker dielectric, which is beneficial to circuit insertion loss, but there's some limitations based on the available space in plane as well as in the height of the total height of the board. Radiation's another bucket listed here. We're not going to consider that a lot today, and so what we've done in the way of the test vehicles that we're looking at tend to concentrate on those types of test vehicles which don't inherently have a lot of radiation loss. A little bit different situation for antennas, obviously, where radiation's intended, but in this case, we're looking at relatively small geometries for microstrip circuits, as well as some strip line test vehicles. So radiation losses are going to be rather limited. So again, continuing on, there's the broad buckets of dielectric and conductor loss, and dielectric loss that we're considering here is dissipation factors from 0.001 to 0.008. So these are not relatively lossy materials, they're relatively low loss materials. That in considering how these impact a circuit, it's important to recognize that in this range, it has a fairly linear effect with frequency. And so as frequency goes up, if it's a 5 mil conductor spacing to the ground plane or 2 mil conductor spacing to the ground plane, the dielectric loss is going to be, again, a linear effect with frequency. Conductor loss, on the other hand, is something that's going to scale inversely with the amount of conductor that's there. And the yellow portion of the curve here, where it's overlapping with the dielectric loss, the yellow portion of the curve showing how conductor loss is going to vary from 50 to 100 microns line width. The next portion is up in the top right of the graph, or top right of the slide here, where conductivity and roughness of the copper have their effects. Now, conductivity of copper is a fairly narrow range, and this, what's shown here in red, is actually a broader range than what we're going to find in electrodeposited and copper foils and rolled copper foil species that we're likely to use in our laminate systems. The loss, on the other hand, is pretty representative of what you can find out there in terms of the range of some of the rougher electrodeposited coppers onto some of the smoother varieties of electrodeposited and rolled copper foils. And combined losses for the whole system, dielectric, line width, conductivity, and roughness are shown in the graph on the bottom right. So in this next slide, we're showing the copper foil impact on insertion loss by way of using a standardized test vehicle. This is the same design, same line width, same impedance, same dielectric height for a 50 ohm line, same dielectric constant in each case. And the only thing varying is the type, whether it be different types of rolled or electrodeposited coppers, and the weight of the copper. So we've got variants that are 18 microns or 12 microns in thickness. And again, the only thing varying between these circuits, by intent anyway, is the copper foil, the particular part number for the copper foil that goes into making the laminate. They're all processed the same way, connectorized the same way, and we get a result that's pretty spread. And still, there's reasons why some of these are going to be chosen over others for reasons other than loss, and that's why we're characterizing all the different possibilities that we build into our qualified products list for the foils that we use in our laminates. A brief description of the foil's respective surface roughness values are shown on the left, and again, this data will be available. So here, this one's a representation of some modeling that we've conducted that varies dielectric thickness by weight, and for the picture, and dielectric constant by color. This is again a set of curves that runs up to 40 gigahertz. The inset on the left is how all the different varieties of laminate materials ranked. It's the same copper foil, and for each of these situations, it's a strip line construction of a 50 ohm characteristic impedance line. So again, there's some different conductor spacings from 4 mils to 8 mils on the ground plane spacing. So that means the line width is going to vary as a function of ground plane spacing, but it's also going to change as a function of dielectric constant. And taking a look at the inset that's kind of in the left corner of the graph, the Pyrolux TK and Pyrolux AP that are shown at the top of the set of curves, they're actually the same thickness dielectric. And what separates them is the dielectric constant. And so the line width of the TK is wider, and it enjoys a better insertion loss figure as a result of all that. The next line is a potential variation on the Pyrolux TK construction that puts us at an even lower dielectric constant than the standard. So at 2.4 dielectric constant for a construction for Pyrolux TK that's targeted at 3 mils gives us 6 mil dielectric spacing between the ground planes and gives us insertion loss that's just about equal to the 4 mil Pyrolux AP or 8 mil ground plane spacing that it's adjacent to. The next line down is another different 3 mil potential construction for Pyrolux TK with a dielectric constant of 2.7. And it models in between the 2.4 DK value and the Pyrolux AP at 75 microns or 3 mils, which is shown next. The last two lines are Pyrolux TK and Pyrolux AP, each of them at 50 microns thickness for the laminate or 100 microns ground plane spacing for the construction. 100 microns or 4 mils. And so this establishes some of the trade-offs that could be used for reducing the board height and also reducing the height. What's possible is that line widths can be reduced. And in the case of the Pyrolux TK at 3 mils versus the Pyrolux AP at 4 mils, it's possible to reduce the height while maintaining the insertion loss performance of the greater thickness option. So some of the other modeling that we leveraged in presenting our materials against conventional laminate types is some work that was done by Intel, US Navy, and ANSYS, and they modeled the effects of a periodic structure on transmission loss, transmission line performance. What they show is that even, and this is irrespective of skew, which we'll get to a little bit later, but even as transmission lines are considered in the case of a board that might be built on a bias relative to an orthogonal orientation to the panel, there's still going to be the case of the transmission lines crossing over individual yarns. Each of these is an opportunity for a reflection, a slight reflection at the discontinuity and impedance, the slight impedance change that's going to happen as the transmission line goes over a yarn or is in between yarns, and it's got different impedance values in each of those locations. Each of those is an opportunity for some small dissipation of power as some of that signal tends to be reflected. In considering the skew part a little bit, there's some phase distortion that's also incurred at that point. So as you're going over regions of different dielectric constant by way of varying proportions of resin and fiberglass, there's some decay variance that happens, and that disperses signal over time a little bit. The results are reduced eye height and eye width from some power loss and a little bit of skew that occurs along the way. We decided to explore that a little bit further in some modeling that was done in-house. If you move to the next slide. So we picked a relatively popular glass style at 4 mils thickness and started considering how this might impact skew for ever increasing data rates. The table on the right shows how for a given data rate, the unit interval is continuing to decrease in time as a function of the data rate continuing increase. And the allowable skew as a function of the unit interval is shown in the right column, the rightmost column there. What this is showing is that quarter of a unit interval, which is the significant, or the part where there's a significant impact on signal integrity for a differential pair, that starts being a real possibility as we're starting to get into data rates above 50 gigabits per second. So we're into that kind of data rate. If you look at the graph on the left, style 3313 is showing a mean value for skew of about 9 picoseconds, where an homogeneous material like the Pyrolux laminates are showing a mean value for skew under half a picosecond. So better than a 10x improvement. The modeling, again, it's a statistical representation shown in the graph of modeling of the impact on skew by varying the position of the differential pair laterally across the substrate pictured for the glass reinforced laminate, as well as rotated from 0 to 45 degrees. So what it's showing is statistically how that skew is supposed to end up happening. So while it's the case that there might be some differential pairs that don't have skew, it's not very likely that there will be all of the differential pairs without skew. It's gonna be an occurrence. So apart from frequency, there are some other ways to get higher data through a differential pair, and more sophisticated protocols for data encoding are among these techniques. So pulse amplitude modulation at 4 different levels in this slide is compared a little. We start to compare it to NRZ or just plain digital. From the bottom right, there's the code representation where the two voltage levels of NRZ are representing zeros and ones, whereas in PAM4 there are 4 different voltage levels that are output, and they're representing codes as shown in the picture. In order to take advantage of PAM4, we think there needs to be a pretty in-depth characterization of insertion loss across frequency for the material that you're working with. So one of the first things that's necessary for PAM4 to work relative to NRZ is to get that same amount of data across the differential pairs. PAM4 is able to do it at half the frequency, but we need to understand that half the frequency is going to give enough signal strength to permit splitting that voltage into 4 different levels rather than just 2. So in the graph on the top right, it's showing a differential pair comparison between homogeneous materials, our Pyrolux AP, and a conventional low loss resin flat glass composite. Now, comparing them at 28 gigahertz shows a pretty significant difference in insertion loss, but we're also interested in the 14 gigahertz comparison. And there, either one of them has enough of a loss benefit relative to the 28 gigahertz number, the 30 dB channel, to enable PAM4. And so the case that either one of these work is a reasonable conclusion. So with respect to what's the advantage of the homogeneous material, we're going to move on and take a look at what some of the effects are of skew. So again, one of the considerations for PAM4 is it's a little bit more sensitive to skew. The curves on the right show the skew effects for a 10 dB channel on top and skew effects for a 30 dB channel. Now, again, it's more likely that PAM4 would be used for a longer channel, a 30 dB channel, the complexity of the hardware I'll show in a few slides. But what's important to note here is that PAM4 at either channel length is going to be much more sensitive than standard digital at 2 levels. In the case of PAM4 comparison to NRZ, the couple of pictures in the bottom left show how the same frequency of PAM4, you can infer that that's going to get you actually to twice the data rate, whereas the first set of pictures shows PAM4 and PAM2 at the same data rate. And if you notice, the PAM2, the NRZ signal, has twice the number of eyes per time, and so these are all consistent on the time scale. So in choosing between NRZ and PAM4, one of the other ways that we're comparing these is that the NRZ signal it's limited at 30 dBs. It's limited to about 15 inches. One of the modeling comparisons we did shows that the NRZ channel for the Pyrolux material set would enable a path length of up to about 22 inches. The other thing it's starting to show is that there's again, at that Nyquist frequency for NRZ, it's showing about a 9 dB advantage, almost enough by itself right there to convert to PAM4. It's got almost enough signal strength at the same frequency. And that's the inference that PAM4, if the material set can be improved upon the incumbent choice, the material set might enable PAM4 to be used at the current operating frequency and achieve twice the data rate throughput. Why you might not use it, again, in the bottom right shows PAM4 hardware is a little bit more complex and takes up a little bit more real estate. These are some of the reasons why it's used for some of the longer channels, but not as often for some of the shorter channels. As well, for the 10 dB channel, it's hard to back that up in frequency enough to get to where the half frequency is not going to have 10 dB less insertion loss. So it's going to be a more useful technique in the physically longer channels. So we've also taken a look at some approaches that use our Pyrolux AP laminates in a hybrid construction. So this is halfway in between a construction made fully using homogeneous materials, no glass reinforcement, and in this case we've got Pyrolux AP paired together with a conventional prepreg. Even in this case, the trace skew is reduced by about a factor of 5. This is some work that was presented a couple years ago at DesignCon. In some other actual hardware built, a hybrid board using Pyrolux AP was much better on the pulse response, with both higher output voltage and less difference between traces, and along the way showing lower skew for the differential pairs. And again, this is an aim to show that as frequencies are going to push up, the PAM4 eye patterns are going to be even more complex than the standard digital eye patterns. With the modeling that we've shown, we're not able not only to quantify the expectations for how much skew and what kind of statistical distribution of skew, but that translates into what the eye diagram ought to look like, and that's been shown here for a couple different data rates. In the conventional material, it looks like the eye diagram's open enough at 56 gigabits per second to work. At 100 gigabits per second, it's looking like a pretty tough ask for the material to support that kind of data rate. For the homogeneous material, however, it maintains a relatively open eye pattern even up to 100 gigabits per second. Again, there's a similar design strategy employed here for the purposes of the modeling and having some useful comparisons for a board that would be built at a similar stack height and number of layers and whatnot. But this clearly shows an advantage for an homogeneous material set where skew and signal integrity are considered together. So we expect that some of our existing laminate products, which are they enjoy a long history in high reliability flex and rigid flex applications, we expect that they can make a smooth transition into some multi-layer constructions. There's also some ongoing new product development work to flesh out the material set for constructions in backplanes and other data server boards. The materials got the potential to reduce power consumption through both lower loss and lower skew performance, reducing the amount of active components necessary and enabling a more consistent performance on the receive end of the signal. Through a reduced number of components, lower power requirements, we're expecting fewer connections and lower operating temperature are going to make for improved reliability in these structures. And what we're pointed at is getting better performance at the design end and at the system end, getting better performance and potentially lower cost out of using better materials, enabling longer channels and through some other applications of the materials, there are some additional kinds of passive structures that can be built. And with that, I'm throwing it over to John to talk about Interra.
Thanks, Jack. So I'd like to switch gears a little bit, and we're still talking about high-speed, high-frequency performance, but we're now going to concentrate more on the power distribution network and power integrity versus signal integrity. So we're going to go over what, in general terms, the power distribution network, why use this technology we call embedded capacitance, and then introduce our product that plays in this area and its benefits. So what is a power distribution network? Well, we need to get power to the ICs to basically so it can perform their function. And it's really, it starts off, basically with the power supply that comes into the equipment. You start with a voltage regulator module, which is actually operating at relatively low frequencies. And then you have decoupling capacitors that are put on the board. And then the power ground planes actually work as part of that power distribution network. And then there's also decoupling caps on the IC package as well as on the IC itself. So there's each as we go from left to right, we're going from low to higher frequencies as we get to the point where we're at the very high switching frequencies of the IC. And so in order to have a good power distribution network, all of these have to operate seamlessly and be able to handle the frequencies they're operating at. So the challenge is that right now traditional capacitors are placed on the surface of the board in parallel to reduce the capacitor bypass inductance, and that's what we're trying to do to get rid of noise and lower the overall impedance of the system. Okay, but what's happening is as the systems are getting, as we're driving more things, such as going from an RZ to PAM4 and going to higher data rates, it's causing a greater demand on the power distribution network, which is causing an increased number of capacitors, growing design and manufacturing complexities, as well as rising costs and reliability concerns due to that. So how do we address those issues? Okay. So at frequencies as low as 100 kilohertz, the dielectric that separates the power and ground planes actually strongly influences the power distribution network. So by using a thin laminate, such as our Interra HKO4, between the power and ground planes, you can reduce a lot of the modal resonances and lower the overall inductance between the planes. Here's an example of again, it's a 2018 edge router. Obviously, this technology has been around. The idea of embedded capacitance has actually existed for several decades. And so it's not a new technology. It started out with a 50 micron, basically FR4 laminate as your power and ground plane. So as you get these planes closer together, you get better performance. But now we need better control of the power distribution network, so we'll be going to thinner dielectrics. So here happens to be an example of a 36-layer networking board, and you can see the very thin layers that are inside the board at multiple locations. And it basically consists of copper, a dielectric, and another piece of copper. The real trick here is that the thinner the laminate, the lower impedance at higher frequencies. So if you look at the left side of this chart, it's really that's in the capacitive range. So as you know anything about capacitors, the overall capacitance is the thickness of the dielectric constant, and then the area you have available. So that'll give you your capacitance value. So the thinner the dielectric, the better the capacitance. And so as laminates go thinner, from let's say 4 mils down to a third of a mil, you see that you get better performance down in the lower frequency range. This is the sub couple of hundred megahertz range. Then you take it to its inflection point, which is typically in the 300 to 400 megahertz range. And then it actually becomes more about the inductance. And so there, the thinner also gives you better performance when you get into the higher frequency ranges. So at this point, I'd like to say what's really happening by making these thin power ground planes is, we call it embedded capacitance, but really it's somewhat of a misnomer, because what we're really doing is lowering the overall impedance of the distribution network by lowering the inductance. So here's an example where we took a 14-layer board and used half-ounce copper in all the layers, and we started varying the thickness between the power and ground planes. So I started out with a very typical thickness, 10 mils between, and they needed 84 total decoupling capacitors to kind of get the job done. If you lower that down to 5 mils, the caps that you need now is only 42. You go down to 4 mils, you get 35, 3 mils, you get 33, and then you get down to 1 mil, and it's 19. It's not truly a linear relationship, but it's kind of close, so that by going from a 10 mil gap, and the 10 mil gap happens many times when people put their power plane and the ground plane and they put the signals in between. And that gives you a pretty, and that's not a good way for power distributions to run. You really want your power and ground planes to be next to each other to get the optimal power distribution network. And so by going from 10 mils to 1 mil, you can remove 77% of the decoupling capacitors. And if you added up the total capacitance of those capacitors, what you'd realize is that you're only replacing about maybe 1 to 5% of the total capacitance with that power ground plane, which we're calling an embedded capacitor. So again, it's really not about adding capacitance, it's about more of lowering the overall inductance of the power distribution network. And what are the benefits of removing all those decoupling caps? Well, you can see it clearly here. This is a picture, the courtesy of Happy Holden, where you have the same board design with and without the embedded capacitance. And you could see that you greatly increase the amount of surface area available. And where do you typically put your decoupling caps? You put it around your ICs, around your packages, because you want to have the lowest inductive loop. So, and that's usually the most valuable real estate, because that's where your highest routing density is. So by removing these discrete capacitors, even though they're getting very tiny, they still have vias and connections, and they still take up some amount of real estate. So you can clearly clean up the board by using embedded capacitance. Also, a lot of people sometimes put their decoupling caps on the back side of the board. And there have been cases where if you use embedded capacitance, you can almost remove that whole second backside placement of decoupling caps and streamline your assembly process. So again, what are the benefits of removing the caps? You get improved reliability. Again, a discrete that's not there can't fail. So, and that includes the vias, and with these small capacitors or resistors, any passive, they can tombstone, which is basically lift off under certain conditions off the pads. So you basically want to get rid of those products. Again, it makes it easier to manufacture because you're eliminating the traces, the vias, the pads, and everything associated with that capacitor. And it basically doesn't cost you really anything to do that. It frees up the space, so now you can either shrink the size of your board, or you can actually add more functional components to the board, whichever you choose to do. Also, you have more flexibility in where you put the remaining capacitors. There was a study performed a number of years ago where once you put embedded capacitor planes in, the bigger capacitors that actually do charge delivery, like your big tantalum caps, can now be placed further away from your ICs, from your packaging, because the power distribution network is so much more efficient at delivering that current, that power, that you have easier places to place. So you don't have to put it so close to the IC package. And again, it also can decrease your capacitor inventory, reduce assembly, inspection, and repair costs. We had one customer look at this because they're worried about the number of SKUs they were carrying and the availability of discrete capacitors. So again, it overall simplifies the manufacturing process. The other thing too is this is a very mature technology, And people have now been doing this, like I said, they started out with 2 mil dielectrics using FR4 fiberglass. That happened, several decades ago. Now people are using these thinner products that are film-based, and that's at least 15 years in use. So, and there's a number of manufacturing sites do this every single day. So it's a mature technology. So our product that addresses this technology, this area is called Interra, particularly HKO4. So our product is a film-based material. It comes in a couple of different flavors. We have our HKO4 J material, which is available in a 1 mil, 25 micron dielectric thickness. And then we have the newer one, which is the M version, which is again also available in 1 mil, basically close to half mil, 12 micron, and we're in the process of developing an 8 micron material, which should be available, later this year into early next year. The copper thicknesses are your typical thicknesses. For power and power distribution, you're typically using 1 and 2 ounce copper, but sometimes for whatever space concerns or whatever, you use thinner coppers like half ounce. So we do also unbalanced construction, so you can have 1/2, and they're available in your typical panel sizes for making circuit boards. And we can do it with both electric positive copper foil, and we can also do it with rolled annealed copper, depending on what the customer wants. It's all certified to the IPC spec for embedded capacitance materials, and we also can supply very low profile copper on our HKO4M product. And what that does is it not only does it give you a smooth copper surface on the capacitor side, but it also gives you a smooth copper on the top side, because some people feel that the return path that the power or ground plane provides also needs to be smooth for signal integrity. So if you're interested, that's also available. So this is the specs of the material, the typical properties. Again, the 1 mil HKO4J and M are pretty much drop into each other. The only difference is the site of manufacturing. So they have a different UL because of that, but they're basically equivalent. So you can see from a thickness standpoint, peel strength, capacitance, dielectric constant, and DF, they're all pretty much overlap each other. They have excellent breakdown voltage because these are polyimide based. They're very strong materials, both electrically and mechanically. They have excellent dimensional stability, and they handle the thermal stress, 288 C, 20 seconds, 6 times solder floats with no problem. Again, polyimide is a very high temperature polymer system, so it can handle. In fact, it's usually the highest rated material inside the circuit board. It's better than the material that's surrounding it, making up the rest of the circuit board. So again, like I mentioned, it's a homogeneous system. It's all polyimide. So because of that, it's very good yields, and it reduces your overall cost to make these layers. And it has very proven high reliability. It actually, a 1 mil polyimide film actually handles much better than a 2 mil FR4 type of fiberglass. It's flexible. It can be handled very well. You still have to have a little bit of precaution when you're handling something that thin, but for the most part, it handles much better than the equivalent materials. Also, you can go thinner without sacrificing electrical performance from a breakdown voltage. Again, because it's a continuous film, you don't have to worry about the things that could happen with fiberglass, reinforced materials that may have voids or foreign material, other things that can cause problems. And again, it has excellent capacitance stability over a very large range of frequencies, temperatures, and voltages. And by its nature, it's inherently halogen free. So there's no halogen agents put into this material. So it's naturally halogen free. So it meets all of the current and future expected standards when it comes to halogens. And again, this is a cross section of it. This is the 1 mil material. This is the J material. You can see that the copper profile that we use is relatively low. Again, we don't want to have any high pot failures or shorting between the layers. As we go to thinner dielectrics, we can also further decrease the copper profile to make sure that we meet all the objectives. And because it's a continuous film, it's a very strong material and very easy to process. In fact, most printed circuit board shops would rather process this material than the thinner FR4 materials or other competing materials. So again, if you look at it, we've also checked it against some of there are other There is at least one other 1 mil material available out there. And so compared to that, you have two things. You have tear initiation and also the ability of the tear to propagate. And again, our material is superior to anything else that's out there as far as resisting the tear from starting as well as propagating through the laminate. And again, this helps with yields and overall reliability. And it's proven technology. Like I said, this technology was introduced well over 15 years ago, and we've passed every single IPC test, thermal, mechanical, pressure cooker, any type of reliability test. In fact, when typically a board is going through this reliability testing, it's the other material that fails before our material does, because it is so robust. And this is done by major PWB manufacturers have all done this test in multiple sites for multiple customers. So we have a wealth of information on reliability of this technology. And this is just, I'm not going to go over all the details in here, but you can see we've gone through all the different, temperature, humidity, bias testing, moisture, insulation resistance. We've actually even done calf testing, because it sounds interesting, say, why would you do calf testing since there's no fibers here to cause the problem? Well, people still want to be comfortable that there isn't a calf-like failure that can occur. So we've gone through and we've done over 1,000-hour testing, 100-volt bias, and so we've been able to, successfully pass the calf testing as well as all these other traditional reliability testing. And again, the other thing too is that there are some other products on the market but as they go thinner, they get more brittle, they get hard to handle, and the yields go down typically as well as the reliability. With our material, we've successfully shown that we can go down to 0.5 mil, and we've even got qualification on the 8 micron material. As we're commercializing, we've already got one customer accept it, and so it shows that because these films are inherently so strong and electrically, mechanically, and thermally, that you don't pay a penalty for going thinner. A lot of people are reluctant going from 2 mil down to 1 mil when these products first came out. Then they realized that the benefit of the 1 mil versus the 2 mil FR4s, and now we're getting people to see, well, if I go even thinner yet, you get the curve I showed earlier showing thinner is better as far as decoupling and doing lowering the inductance of the system, that people are now looking at the 12 micron version, and in some cases even going thinner. The other thing about a polyimide base versus the other materials that are out there is that polyimides are very stable over a large frequency range. So it doesn't make, so in the operating range that we're interested in, where this power ground is doing its thing, it basically is flat compared to other materials, which their dielectric constant starts to change with frequency. And so they start seeing, that they get a little bit lossier, as well as they have to see a drop in capacitance because their dielectric constant actually goes down at higher frequencies. And the same thing too is the temperature coefficient of capacitance is much more stable versus other materials. This just shows you overall that under normal operating conditions and even extremes of operating conditions, the material will behave consistently time in and time out. So in conclusion, embedded capacitors allows you to remove those surface mount capacitors. And if you just did if you tried to justify this technology just on the amount of capacitors you get off the surface, that could be justification enough. But not only do you get rid of those surface mount capacitors, you improve the reliability because they're no longer there, and also the vias are gone. It's actually easier to manufacture a board because now you're and from a design standpoint, it's just a power ground plane. You don't have to do any special, you don't have to embed capacitors. It's really basically just a very thin power ground plane, and you just have to remove those discrete capacitors. And there's several simulation tools out there to show you how many capacitors you can actually remove once you use this technology. And also, again, frees up that valuable board space, especially as densities are increasing. And that's a value just in and of itself. It allows you to make thinner boards and increase your layer count in the same thickness. We've actually had customers do this technology just so they can make the boards, they can actually squeeze some more signal layers in the same overall board thickness by going from a 4 mil or larger power ground plane down to 1. And that's be very valuable. It also simplifies your design and reduces costs overall. The material now used to be a little bit of a premium, but with the cost of the materials that the rest of the boards are going into, is like your, the high performance materials that these boards are being built on, the delta now is almost irrelevant between the two technologies. And then again, our particular offering has excellent mechanical properties, proven reliability over decades, able to go thinner, excellent capacitance stability, and it's inherently halogen-free, so there's no worry about meeting any sort of requirement for that. And with that, I'd like to turn it over to Nancy Lima for questions and answers. Thank you.
Thank you, John. All right. Well, we have a few minutes left, and we do have a few questions here. So, John, this question is for you. The question is handling and damage an issue on the thinner material?
No, it actually, one of the things we have to remember about these power ground planes is that they're almost 80% retained copper typically. So you really have just the clearances and the anti-pads and the pads. And so it's not, so most of it is copper, but because these films are inherently very stable and very strong, there really isn't a handling issue. There's some tricks that you do about the way you line up the circuits top to bottom from each other so you don't have like a knife edge. So you might offset or grow like the bottom pad a little bit different than the top pad. So some tricks in design, but for the most part, this material is very robust and the high pot yields are excellent. So really the yields, major board shops do this every day with very like 99% plus yields with no handling problems.
Great, thank you. The next question, I'm not sure if this is for Jack or John, but what is the decay of your embedded capacitance laminate?
Yeah, typically it's around, as shown on the chart, about 3.4, 3.5 in that range. And again, it's because it's about, obviously if you wanted to make a capacitor, you would if you truly want to make discrete capacitors, you go to higher dielectric constant. You can do that by adding various ceramic fillers. And that's something there are some materials on the market that do that, but that's if you're looking for discrete. When it turns out when it comes to this high-speed decoupling, the thinner is overall a bigger impact than the dielectric constant.
Thank you. The next question is, what is the maximum number of layers that the embedded capacitance can go to in PCB boards?
Maximum number of layers?
Yes, embedded into capacitance.
Yeah, typically these, usually most people build symmetric boards. And so it's basically any power ground plane in there can be substituted with these thin dielectrics. And so I've seen designs that have used typically 3 is like the minimum. And they're usually put on layers like 2, 3, and N-1 and N-2. So lots of times they're on the outside to lower the overall inductance. But I've seen as many as typically 3 is very, very common. 5 is used quite a bit. We've seen as many as 7 to 9 layers. There's really not a restriction on the number of layers that you can put inside a board. Obviously, these and these have been tested. The rest of the board is made up of fiberglass material, and so obviously the film is not as strong as the fiberglass from a mechanical standpoint. But even the ratio, since these are only 1 mil dielectrics, the bulk of the rest of the dielectric is all fiberglass. So again, we haven't seen any problem going to very high amounts of material. But again, typically I'd say 3 to 7 is very common.
Thank you again. All right, the next question we have is, this is a question to the Interra product. What is the impact of thickness variation of the dielectric material on capacitance? And what is the thickness tolerance of the HKO4 products?
Yeah, typically, obviously, it's linear. So as the thickness varies, so does capacitance. So if you have a thickness variation of 10%, you're going to see the 10% difference in capacitance. But we hold our thicknesses much tighter than that. They're typically less than 5% variation. Typically, it's usually only a couple of percent. And so that type of variation is not going to cause any sort of problems with the performance of the laminate.
Okay, thank you. Again, we have another question on Interra. What is the reason of stable capacitance versus temperature performance in a polyimide compared to an epoxy-based? Is this something to do with CET of materials? Okay.
Yeah, what it has to do with because the polyimides have a very high glass transition temperature, so they really don't change, and also they have they have much lower loss characteristics than a lot of other materials. And so what happens is that because they're so thermally stable, that you don't see much change in it over the ranges that we're typically going to operate at. And the same thing with the frequency range that we're operating at. So again, over the because polyimides can go up to very high frequencies with very low loss characteristics. So just by the nature of a polyimide versus a traditional thermoset material, it has much more overall stability.
Great, thank you, John. All right, and the next question is there a process manual that includes how copper features overlap in equipment fabricators need?
Yeah, typically there are when a fabricator first learns or is learning how to do this technology, there are some process guidelines that we share with people on some tricks of the trade, so to speak. Typically, you may only have to offset the top and bottom conductors by just a few microns, several, just 10 to 15 microns. It's not a big deal. And so, and also the border pattern that people pick. Lots of times when you're making thicker laminates, you may have a diamond pattern or a solid pattern. And so if you can have more copper on the border pattern around it, you can stiffen up the laminate to make it easier to handle as well. So these are things that, because most of the board shops have used this technology for several years, they've already have that in place. So I'd be very surprised if whoever is asking the question, if one of their fabricators isn't already using this technology every day.
Great, thank you.
Most people now have thin. Most people have thin guides, in their wet process equipment. Most people have now the guides in place so they can handle very thin materials going through the, through their process without having any sort of problem. So the infrastructure is in place to handle these thin laminates.
Perfect, thank you. Jack, this may be a question for you. Does dielectric constant also affect the widths of these transmission lines for a particular characteristic impedance? If so, how?
Absolutely does. So for a given ground plane spacing, the lower dielectric constant, you use in the dielectric laminate, the wider the trace is going to need to be to still be 50 ohms characteristic impedance. The other thing, and this is a little less, I'm not sure that we've explored this as in depth to this point, but with some of the lower dielectric constant composites that we've got, in particular the Pyrolux TK, it's possible that some of that additional line width can be made by moving the lines actually closer together, because it's lower dielectric constant material between the two adjacent traces. There's going to be a little bit less capacitive coupling between the two traces. So at a given spacing, for instance, there's going to be less crosstalk. So there's maybe an opportunity to move those lines closer together while making them wider and achieving lower insertion loss. Again, at a given ground plane spacing.
Great, thank you so much, Jack. Well, we are at the top of the hour, and we will try to get to some of these questions, possibly send them out. We thank you for attending today's webinar. And again, we will share this recording to all the participants in the coming days. Thank you so much. This concludes our webinar for today. Thank you, John and Jack, for presenting today.
Thank you. Thank everyone for gathered today. Bye now.
Take care.